We've been tracking 3i Atlas for several months, but there's something new and very interesting that's piquing a lot of people's attention, getting a lot of people's attention right now.
3i Atlas is once again in the headlines, not because of something it has done, but because of what has been found on it. Scientists have detected water unlike anything seen before, with a composition that doesn't match what we observe in our solar system. The finding is clear, but the explanation isn't. If this water didn't form under familiar conditions, then where did it come from? And what does that say about the object carrying it? Unlike anything seen in comets or asteroids from our own solar system, this water seems heavily altered, with a pattern of isotopes that makes it stand out. The measurements come from the James Webb Space Telescope, whose ability to dissect light into its chemical fingerprints has opened a new level of precision in observing distant objects. Through spectroscopy, scientists were able to identify deuterium not only in water molecules associated with 3i Atlas, but also in methane. In the case of water, roughly 1 in every 100 hydrogen atoms was replaced by deuterium. In methane, the ratio was even more striking, closer to 1 in 30. In the Sun and in gas giants like Jupiter, the fraction of deuterium is about 1 in 50,000. Even on Earth, where processes have slightly enriched this isotope, the ratio is still only modestly higher. Against that backdrop, the composition of 3i Atlas appears profoundly out of place. Deuterium is not just another ingredient in cosmic chemistry. It carries with it a history that stretches back to the earliest moments of the universe. Formed within minutes after the Big Bang, it is fragile, easily destroyed in the interiors of stars, and therefore its abundance becomes a sensitive marker of environmental conditions. In astrophysics, deuterium functions like a tracer, a subtle but powerful indicator of where and how material formed. High concentrations are typically associated with extremely cold environments, where chemical reactions favor its incorporation into molecules. That is why astronomers pay close attention when its levels deviate from expectations. It is not merely a chemical curiosity, it is a clue. Faced with the data from 3i Atlas, the first instinct is to search for a natural explanation. One possibility is that this object formed in a region of space far colder than anything commonly encountered in our solar system. Perhaps it originated around an ancient star in the deep freeze of interstellar clouds that existed billions of years ago. Some interpretations suggest an age of 10 to 12 billion years, more than twice the age of our own solar system. In that scenario, the elevated deuterium would be a relic of those primordial conditions, preserved across unimaginable stretches of time and distance before arriving here. However, the situation is far from straightforward. The same observations that reveal high deuterium levels also point to the presence of heavier elements, such as carbon and oxygen, elements that require multiple generations of stars to produce. In the earliest epochs of the universe, these heavier elements were scarce. Reconciling a highly enriched deuterium signature with a composition that includes significant amounts of carbon and oxygen introduces tension into the model. If the object truly formed in such ancient environments, there should not have been enough heavy material to account for what is being observed. The explanation begins to strain under its own assumptions. This is where the sense of puzzle deepens. The deuterium anomaly does not exist in isolation. It joins a growing list of features that, taken together, suggest that 3i Atlas does not behave like a typical comet or interstellar object. Observations have indicated the presence of jets, streams of gas erupting from its surface, that appear to be arranged in a surprisingly symmetrical pattern. In most comets, such jets are driven by localized heating, emerging from irregular patches of ice. They are often chaotic, uneven, and difficult to predict. Symmetry, in this context, is not impossible, but it is uncommon enough to raise questions. There are also peculiarities in the object's trajectory that continue to draw attention. Unlike typical comets or asteroids, which can approach the Sun from a wide variety of angles, 3i Atlas appears to follow a path that falls within a surprisingly narrow range relative to the plane of the planets. While gravitational interactions can certainly produce unusual orbits, the degree of alignment observed here is striking enough to warrant a closer look. It does not, by itself, prove anything extraordinary, but it adds a layer to the growing list of characteristics that challenge simple explanations. Each piece of data, taken on its own, could be dismissed as a quirk or an anomaly, but together, they form a pattern that defies easy classification. Equally intriguing is the chemistry of the object's emissions. Early spectroscopic analyses revealed an unusual abundance of nickel relative to iron, a ratio that differs sharply from what is commonly found in most asteroids and comets. Normally, nickel and iron appear together in similar proportions, making this disparity stand out. On its own, this odd ratio could be chalked up to measurement uncertainties or rare natural processes. Yet, when considered alongside the extraordinarily high deuterium content and the presence of structured jets, it paints a picture of an object that does not fit comfortably within established categories. Each anomaly amplifies the others, creating a mosaic of features that seems deliberately intricate, almost as if the object were designed to defy expectation. At this point, the discussion naturally shifts from mere observation to interpretation. Some scientists emphasize caution, noting that anomalies do not necessarily imply artificiality. Yet others, like Loeb, argue that when multiple anomalies appear together, chemical, isotopic, and structural, they invite broader consideration. Loeb points out that deuterium is not only a naturally occurring isotope, it is also a critical component in advanced energy systems. On Earth, deuterium combined with tritium is used as fuel in experimental fusion reactors, representing one of the most sophisticated human technologies. Its unusual concentration in 3I Atlas, coupled with other irregular features, raises the tantalizing question: could there be processes at work beyond what we typically observe in natural objects? From that starting point, Loeb raises a provocative question. If an object exhibits an unusually high concentration of a substance that is useful in fusion, could that abundance be more than incidental? Could it represent a technological signature rather than a purely natural one? He extends the idea further through analogy, invoking the concept of a Trojan horse. In classical terms, a Trojan horse is something that appears ordinary on the outside but conceals an unexpected presence within. Applied to an interstellar object, the analogy suggests a striking possibility that what seems like a comet or asteroid could in fact be a vessel or container, carrying something far more complex than its exterior reveals. It is not presented as proof nor as a prediction, but as a way of framing the object's unusual features in a context that encourages open-minded examination. The notion is provocative because it invites observers to look beneath the surface, both literally and figuratively, asking whether familiar categories of natural phenomena are sufficient to explain what is seen. Within this speculative framework, an interstellar body could function as a vehicle, traversing immense distances while harboring technology, materials, or even informational payloads concealed within a seemingly natural structure. Every anomaly, the alignment of its trajectory, the unexpected isotopic ratios, the unusual chemistry, and the structured emissions, becomes part of a broader pattern that makes this possibility conceivable, if not inevitable. Loeb emphasizes that such speculation is not a conclusion. It is a lens through which to consider anomalies that resist conventional explanation. The metaphor of a Trojan horse, in this context, transforms the object from a simple visitor from another star into a puzzle that challenges assumptions, inviting scientists to ask a question that lingers at the edge of current understanding. Could nature alone produce something so systematically unusual? Or is there more hidden beneath the surface? The challenge with such speculation lies in distinguishing between what is conceivable and what is supported by evidence. Nature is capable of producing phenomena that appear highly structured or statistically unlikely without invoking design. Chemical processes in extreme environments can yield unexpected results. Physical systems can generate patterns that mimic intentional organization. The history of science is filled with examples where initially puzzling observations eventually found natural explanations as data improved and theories evolved. At the same time, the presence of anomalies is not something to be dismissed. Scientific progress often begins at the edges of understanding, where observations do not align with predictions. The key is to approach these discrepancies with both openness and rigor, to consider multiple hypotheses while maintaining a commitment to evidence. In the case of 3I Atlas, the data currently available does not provide direct support for an artificial origin. There are no detected signals, no resolved structures, no unambiguous indicators of technology. What exists instead is a set of unusual characteristics that invite further investigation. That investigation, however, is constrained by circumstance. 3I Atlas is a transient visitor, moving quickly through the solar system and now receding from view. The opportunity to study it in detail has been limited to remote observations. There has been no close-up imaging, no physical sampling, no chance to directly analyze its surface or internal composition. In principle, such an object could have been intercepted by a spacecraft, allowing for detailed measurements that might resolve many of the current uncertainties. In practice, no such mission was ready in time. Interstellar objects like 3I Atlas are rare, and each encounter represents a chance to examine material that formed in environments far beyond our own system. These objects carry information that cannot be obtained in any other way. Traveling to their points of origin would require journeys lasting millions or billions of years. Instead, they come to us, briefly, offering a glimpse into regions of the galaxy that would otherwise remain inaccessible. The fleeting nature of these encounters highlights the importance of preparedness. Future observatories, surveys, and potential interception missions could transform how such objects are studied. With earlier detection and faster response capabilities, it may become possible to approach these visitors, to image them in detail, to collect samples, and to directly test the hypotheses that now remain speculative. Each improvement in observational capability increases the chances of moving from inference to confirmation. In the meantime, 3I Atlas remains an unresolved case. Its deuterium enrichment challenges conventional models of formation. Its additional anomalies complicate the picture further. Its origin, whether in an ancient frozen region of space or in some other environment not yet fully understood, remains uncertain. The more speculative interpretations, including the possibility of technological involvement, remain unproven, existing at the boundary between scientific curiosity and imaginative extension.